One of the topics that often arises in statistics is whether to work with the original data or modify the values in some way for some reason. Such data transformations are common, and they're typically done for two reasons. First, to create more useful descriptive statistics, to create a better metric or representation of the data to help us understand the system we're studying. This is most often done when the range of raw values is extreme, or when there is a more intuitive way of thinking about the data than by using the actual values measured. In this video, we'll look at some examples of familiar metrics, which are actually transformed versions of the raw data that defines them. The second reason to transform data is to aid in statistical testing, to modify a dataset which violates the assumptions of the test we want to use into a new set of data that does not, so that tests can be done. The validity of most statistical tests relies heavily on the properties of the numbers being used obeying these assumptions, so making sure that we're working with numbers that do is important. In this video, we'll look at some situations where this comes up and give a brief summary of 6 of the most common transformations people tend to do. First up, descriptive statistics. Some things we measure vary across a wide range, but it's verbally, and maybe even typographically, awkward to talk about comparing values of the same thing across tens, thousands, millions, billions, etc. Instead of talking about millions, billions, and trillions, and hoping that people remember how many zeros that is, it's much easier if there's a new metric that condenses this scale into something easier. As an example, in chemistry, the concentration of hydrogen ions in a solution can vary from extremely dilute, the hydrogen ion concentration having a molarity of 1/10,000,000th, to very concentrated, the hydrogen ion concentration having a molarity of 1/10th. And this radically alters the properties of the solution from being very basic in the first case to very acidic in the second. The solution, pun intended, has been that instead of talking about these concentrations directly, we calculate a metric called pH, which is the negative log base 10 of the hydrogen ion concentration. It's not very intuitive at first, but this transformation has great properties. Water has a hydrogen ion concentration of 1 in 10 million, which is 10 to the negative 7 if written using scientific notation, which ends up giving a pH of 7. Bases have lower hydrogen ion concentrations, which end up producing higher pH values than the 7 for water, up to around 13, which is almost no free hydrogen ions at all, which makes it very basic. Acids have higher hydrogen ion concentrations than water, which end up producing lower pH values than the 7 for water, down to around 1, which is a solution with so many free hydrogen ions that it's very acidic. The math is a bit weird because almost nobody likes negative numbers or logarithms, but once used for a while, the pH values become a great descriptive statistic. The second example comes from the Richter scale used to measure earthquakes. The shaking from earthquakes can be measured by the amplitude of the waves seen on seismographs, and the example seismograph shown here demonstrates that the raw amplitude values can vary over a wide range. Instead of using these raw amplitudes, we calculate the magnitude using the log base 10 of the measured amplitude divided by a reference amplitude. This way, each whole number of the magnitude is 10 times higher in raw amplitude, which is actually 31.6 times higher in energy. That's why when we look at magnitude numbers, like these ranging from 2 to 8, the severity varies widely. A magnitude of 2 is hard to feel, but a magnitude of 8 is catastrophic because it represents a measured amplitude a million times higher, which corresponds to 1,000,000,000 times more energy released. Instead of newscasters talking about millions or billions of times difference in amplitude or energy, they can just talk about single-digit Richter scale number, and after people hear this a few times growing up, most understand this scale of transformed amplitude values just fine. The log transformation is very common, but not the only one used. For example, musical systems vary across the world, but Western musical pitches are often defined by when the frequency doubles, an octave. Of course, there can be an arbitrary number of steps along the way from one octave to the next. A common number of steps in Western music is 12. For example, that's the one used by pianos. The set of 12 keys shown is repeated along the length of the piano for each octave. What's interesting is that each step is equal and multiplicative, with the same change for each of these 12 notes in an octave to get to the next set, which starts with double the frequency in hertz. The box shows the actual frequency in hertz for middle C, and each higher note up to the next note called C. Trying to talk about the actual frequencies would be super complicated, so musicians use this letter system instead. Because these steps are equal and multiplicative, each higher note is the 12th root of 2 times the frequency of the previous one, so that after 12 steps, the frequency is doubled. Obviously, nobody wants to think about either 261.6 Hz for middle C or the 12th root of 2 when talking about music, so these values were transformed into this letter metric, which is much easier to use. In practice, musicians actually define a single standard frequency, a concert pitch, and adjust the other frequencies around that. In a very cool historical anecdote, the widespread use of the modern concert pitch being 440 Hz dates from 1919 when the Germans were forced to accept a concert pitch of 440 Hz for the A above middle C as part of their surrender terms to end World War I. Seriously, it's Article 282, Part 22 in the Treaty of Versailles. Follow-ups by professional organizations codified this into the standard most commonly used today. Some places still use different concert pitches. Anyway, the point is that the transformation from Hertz to a letter system allows musicians to work with a much better descriptive statistic for their musical notes. pH, the Richter scale, and musical notes are just some of the transform metrics we use. Some other examples include decibels for sound volume use a log-based 10 scale. This is partly because the human ear is incredibly good at detecting super faint sounds that are thousands of times quieter than the other sounds we also deal with. Photographic f-stops divide the aperture diameter by the square root of 2 at each stop. This is the physical mechanism to reduce the amount of light by half in a pre-digital camera and influences a variety of other aspects of the photograph. Digital cameras don't have physical mechanisms like those that require the f-stop nomenclature, but the field has been using them for so long that these values have transferred over. Astronomical apparent magnitude, abbreviated AM, is used for star brightness, and each value of 1.0 is 1 divided by the fifth root of 100 times brighter or fainter as measured in terms of raw photometric brightness. The brightness for nearby Vega is set to an apparent magnitude of 0.0 to calibrate the scale. Awkwardly, brighter objects like the planets get smaller and negative values, but almost all stars are fainter than Vega and they get larger positive values. The scaling is needed for a similar reason as decibels. The human eye is very good at detecting extremely faint objects, but the weirdness of the scale, where fainter things get larger numbers, was done to match the modern values up with the Roman astronomer Ptolemy's scale from about 2,000 years ago, which had been used for a long time. The main point of all these kinds of transformed values is to replace awkward actual values with more useful ones to facilitate communication and understanding. That takes care of the descriptive statistics side of transformation for this video. Next up, statistical testing. Whenever we do a statistical test, it will have assumptions about the population that must be met to avoid extra type 1 or type 2 errors. If the mathematical model being used to generate the p-values of a test requires a data distribution that doesn't match the actual distribution of the data values, then these kinds of errors can be very frequent. For this reason, the preliminary step in many analyses is a test of the sample data to ensure that it fits the assumptions of the test. We can think of this as a flowchart. First, we collect the data from our system we're studying. This is typically accompanied with some idea about the kind of test we want to do, comparing means, looking for a trend, whatever. So then we ask whether the collected data meets the assumptions of the test we want to do. If it does, then we can go ahead and do the test with the raw data and there's no need for transforming the values. If it doesn't, then we would typically transform the data values and recheck the assumptions. If the new transformed values meet the assumptions, then we do the test with the transformed data. If the new transformed values don't meet the assumptions, then we have two choices. We can either go back to the raw data and transform it again using a different transformation, or we can give up and move on to a different method. Usually we would try several transformations because these different methods are often less powerful or more complicated to interpret. It's usually better to work with the usual techniques that people are familiar with than get forced into more esoteric techniques. So what kinds of assumptions are the ones we need to worry about? The most common reasons for needing a transformation include the following. Data having a normal distribution is required for the 66, 95, 99 standard deviation interpretation, where those are the percent of the values within 1, 2, and 3 standard deviations of the mean. Data having a normal distribution is also needed for the f-test, t-test, and ANOVA techniques. When the data is skewed or non-normal, these techniques can give incorrect conclusions. While the t-test and ANOVA are somewhat robust against minor violations of this assumption, the f-test is very sensitive to deviations from normality. Symmetric distributions for the f-test, t-test, and ANOVA are also an assumption. If the data is normally distributed, this will be met automatically, but slightly non-normal distributions can still work for the t-test and ANOVA as long as the data is symmetrical. It's typically best to make sure the data is normally distributed because this will cover the symmetry requirement as well. Equal variances are a requirement for homoscedastic t-tests and ANOVA analyses. If the variances aren't equal for two samples, we do have the option of a heteroscedastic t-test, but there is no direct analog of the ANOVA for heteroscedastic data, and a much less powerful technique like the Kruskal-Wallis test has to be used instead. Correlation and regression analyses require a linear data pattern with normal distributions and equal variances for the residuals around the best fit line. This is very important because using linear methods on nonlinear data can be completely misleading and miss the actual process causing an observed relationship. The normal distribution and equal variance requirements come from the fact that we tend to use ANOVA or t-test methods to estimate the statistical significance of observed slopes and relationships. Too many people just plug their XY data into a correlation or regression model without making sure to check all these assumptions. Finally, transformations can be useful for reducing the impact of outliers without having to exclude them. Ideally, we'll use all the observed data when making estimates and predictions, but outlier values can have a disproportionate effect on the calculations we make. Transforming the data can allow us to use all the data rather than having to make potentially arbitrary decisions about whether to include weird data points that we think might not be relevant for our purposes. Okay, so what do these transformations look like? When transforming data for a statistical test, there are three main requirements that must be met. First, the transformation must preserve the relative order of the data values. The sequence could flip, but the order must be preserved. For example, a transformation like this, where A is less than B is less than C, and the transformed values are the same, is good. So is this one, the key being that the transformed value of B is still in between the transformed values of A and C. But this transformation would not be valid because the sequence of the transformed values isn't ABC or CBA. The middle original value doesn't end up in the middle of the transformed values. Second, the transformation must be continuous. That is to say, there are no gaps or untransformable values. Every value in the original dataset has to be able to be transformed using our chosen method. Third, the transformation must be fully invertible or reversible. There must be a way to get back to the original data from the transformed values. This is essential because we usually want to take conclusions based on our transformed values and discuss their implications on the original values, which is impossible if we can't untransform the values. Finally, our transformation is given by functions such as f of x equals log base 10 of x or f of x equals the square root of x. We explicitly specify an equation or detailed procedure to use to do the transformation. Let's look at a simple example to see how these three requirements work. For our simple example of a valid data transformation, imagine we have a data set and apply the following transformation. F of x equals 1/2 of x plus 7. If x is 30, this would be f of x equals 1/2 of 30 plus 7, which would be 22. The transformation would transform a value of 30 in the original dataset into 22 in the new transformed dataset. First, this equation preserves the order of the numbers. Smaller original values will always result in smaller transformed values compared to larger ones. Second, this equation is continuous. Any number can give a valid outcome. There isn't a value that won't give a result if we apply this equation to it. Third, this equation is fully invertible or reversible, with every unique transformed value mapping back into a single pre-transformation value. We can actually see this last part by defining an equation that takes values from the transformed dataset and turns them back into values in the original. F prime of x equals the transformed x minus 7 and then multiplied by 2. If the transformed value is 22, then f prime of 22 would be 22 minus 7, which is 15, times 2, which is back to 30. This kind of transformation isn't really a useful one, since it wouldn't change the statistical shape of a data distribution, but it does show the three factors that a more useful transformation has to have. Now let's look at 6 of the most common transformations used in analyses. The first transformation is the logarithmic transformation. There are two common log transformations used, either log base 10 or the natural log. Either of these can be reversed by exponentiation, using base 10 or e for each of these. This transformation condenses a huge range of values, especially for datasets with a positive skew. Log transformations will tend to reduce the magnitude of larger original values much more than smaller original values, bringing in a long tail in the positive direction. For example, a log base 10 transformation turns a set of numbers in the range from 15 to 10,000 into a range of values from 1.18 to 4. Note that 10,000 is 10 to the 4th power, which is why the transformed value of 10,000 is 4. Because of this reducing property, the log transformation is used very often to equalize variances when comparing groups, since the variance often increases with the mean. For example, the ANOVA requires equal variances, yet is used to test for differences between means. If the means are genuinely different, then the variances may therefore differ as well, so a transformation like this one equalizes the variances and allows us to do the ANOVA. There are two commonly used log transformations. The log base 10 is nicer for descriptive statistics, whereas the natural log has nicer mathematical properties. Both are used widely, but the log base 10 is usually better for making figures to show the transformed values. Both of these are equally effective at straightening out curved data patterns and XY plots where the curve is due to an exponential process. Logarithms are undefined for values of 0 or less, so if the data has negative values, or 0, we can add a constant big enough to make all the values positive prior to applying the log, making a two-step transformation which is still reversible with exponentiation followed by subtraction. The second transformation is the square root transformation, where the transformed values are just the square roots of the original data. This transformation is very similar to the logarithmic transformations, with the mathematical benefits and limits pretty much the same, so I've relisted those again here in lighter text. The main statistical difference is that the square root transformation is more limited for highly skewed values over extreme ranges. For example, the square root transformation of the range 15 to 10,000 now gets transformed into 3.87 to 100. Extremely large values are not reduced as much as they were in the logarithm example. Although having similar utility as the log for doing analyses, the square root transformation is not as good for displaying data, however. If you need to shrink a wide range of values for a figure in a way so that people can understand the axes easily, the log-base 10 transformation is much better. The next transformation is called the box-cox transformation, which uses the equation shown. f of x equals a fraction where the numerator is x raised to a chosen power lambda minus 1, all divided by the lambda term. This transformation is similar to the previous ones in that its main benefit is making skewed data more normally distributed. The box-cox transformation is much more complicated in at least one sense, however, because the lambda value is chosen based on the data. Trial and error or a fancy algorithm is used to pick a value of lambda which makes the data normal. This can be complicated and typically requires a computer. This process of choosing lambda can lead to two interesting quirks. If the best lambda is 0, then the equation can't be used, because both the numerator and denominator would always end up as 0, so we would use the natural log transformation instead. If the best lambda is 1, then the equation just becomes the original value minus 1. This shifts the values downwards by 1 on the number line, but leaves the shape of the distribution unchanged. This is because the data is already normally distributed. Despite the apparent downside compared to the previous two transformations, this transformation will sometimes work for data that they don't, and is therefore often used in public health, economics, and manufacturing or quality control studies which face skewed data values. The next transformation is the Arcine square root transformation. f of x is the arcsine of the square root of the data value x. The two equations shown are the same. There's just two different notations for the arcsine function. In contrast to the previous transformations, which were about shrinking distributions, this one widens distributions. That makes it useful for cases where the data is too centralized compared to the normal distribution. The arcsine square root transformation is most often used for proportion or percentage data because it equalizes the variance across the entire range. This is because the raw variance is highest for proportions closest to 0.5. By influencing the edges of the distribution more, the arcsine square root transformation balances the variances so that homoscedastic methods can be used for the entire range of proportions. The main use of this transformation is to allow estimation of confidence intervals for proportions, but it is not recommended for proportions very close to 0 or 1 because at the very edges the equation can become inaccurate. The arcsine square root transformation is used for fields which estimate rates, for example epidemiology, and especially for survey studies where the data is on a Likert scale or other agreement response scale, for example political polls. That's because these types of data sets naturally produce raw proportions. The next transformation is the ZCORE transformation, where f of x is the difference between each value and the mean divided by the standard deviation. This converts every value into a new one, which represents how many standard deviations above or below the mean it is. Unlike the other transformations in this video, the goal of this one is not to change the shape of the data distribution. Rather, this transformation allows comparison of values, relative to the mean of variation, in groups that differ in magnitude. Note also that the variance typically increases in groups with larger mean values, so this transformation can be very useful for dealing with that scaling issue. Ideally, the data should be normally distributed to make comparisons of z-scores most useful. But lots of datasets have this property, and we still want a good way to compare relative values within sets with different means. This transformation is therefore used to create a common scale to compare values on. That is to say, is the value unusually large or small relative to the others in its group? Here's an example of how this is used from my personal experience. I'm a faculty member, and we often review sets of as many as 90 scholarship applications, but reviewing all 90 would be too much for any one person. So we do something like having a committee of 6 people review 30 each, so that each application gets reviewed by 2 people, and we use the average score to rank the applicants. Unfortunately, we discovered a while ago that different reviewers varied widely in their average score and how variable their scores were. This meant that students getting scholarships was based on whether they got lucky and got assigned to the reviewers that gave high average scores. To address this, in my department, we now use the Z-scores from each reviewer, which indicates how good the review was relative to the average review score they gave, and this eliminates the problem. The other, less mathematical departments on campus don't do this, so they end up having less fair scholarship programs. In addition to allowing this kind of scaling, the ZCORE Transformation allows easy identification of outliers, unusually small or large values, using a more objective method than just eyeballing them. It takes into account the overall variation when identifying unusually different values. The ZCORE transformation also allows easy approximate statements, since z-scores of plus or minus 1, 2, and 3 encompass 66%, 95%, and 99% of the data. As long as you have data that's normally distributed, or at least close, the z-score method is one of the best ways for comparing relative values across different datasets. The last transformation for this video is the rank transformation. For this, the function takes a list of original values, and the values are translated into a rank, first, second, third, etc. The ranks can be based on smallest to largest or vice versa, but the key is that there's an order. This transformation does not create a normal distribution like the other transformations. In fact, it essentially removes the shape of the data distribution completely. This transformation removes the undue influence of skews in data or outliers, because these just end up being ranked first or last, and without a magnitude associated with them that balloons up any calculated statistics. The main benefit of the rank transformation is that it allows non-quantitative categories, like small, medium, or large, to be studied while preserving their order or sequence without introducing arbitrary magnitudes. There are plenty of situations in which we can sort data into ranks, but there aren't meaningful numerical differences between the values. Think about lists of best movies or hardest jobs. Which numerical value can we place other than just knowing which are better or worse than others? Unfortunately, with rank data we can't use a lot of the standard statistical techniques like t-tests or ANOVA, but rank data allows the use of a set of rank-based statistical tests which are less powerful but more robust versus error due to violations of assumptions. Not all datasets can be transformed into normal distributions using the previous transformations, but almost all can be made into ranks. It discards a lot of the information, but at least the transformed data works with these rank-based methods. And this method doesn't have the risk of violating the mathematical assumptions behind methods that require normal distributions. This video has looked at 6 examples of transformations, but there are lots of other transformations out there, although they're less common than the ones in this video. Lastly, there are a few very important things to keep in mind when doing transformations. The formal conclusion of a statistical test on transformed data will differ. For example, a t-test would indicate a significant or non-significant difference in the means of the square roots instead of the actual values if you use the square root transformation. The interpretation may remain the same, however. For example, an ANOVA may show that one group has larger mean square root values, and this would be conceptually the same as that group being larger in some manner, even if we didn't have evidence that the raw values themselves are larger. Also, any confidence intervals, figures, or predictions apply to the transformed values. They must be transformed back to make conclusions about the original raw values or patterns. Finally, if your data doesn't need to be transformed, it's usually best not to. The only real exception to this is if you're working in a field with norms and social traditions that demand the use of certain transformations. Transformations are very common in statistics, and I hope this video helps make sense of them. As always, there's a PDF of this overview slide on the StatsExamples website, where you can also find other videos. In addition to liking and subscribing, if you know someone who could benefit from this video, please share it with them.